Hi again, this is Nick Marchuk, and this is the third video of my series on designing a printed circuit board for a PIC32 in Eagle. In this video, I'll show you how to take the schematic and turn it into a printed circuit board layout, and turn that layout into Gerber files that we can then send to a manufacturer to be produced. I'm going to order my PCBs from a company called PCB that you see here. But there are several options when you do this, Seed Studio and Osh Park and Advanced Circuits, and then local companies as well. So don't feel like you have to use PCB. This is just one example. First, let's talk about what is the physical printed circuit board. See if I can find a picture of this will kind of do here, this little thing. So the printed circuit board itself is a solid core of FR4, which is a type of fiberglass. And on the top and bottom side are copper layers. And then on top of that is solder mask, which is a solder phobic paint. And then printed on either side of that could be silkscreen, which is usually a white text. So if you look at a printed circuit board and you see a green surface, the green paint, that's the solder mask. And it's there so that when you add solder to a copper trace, it sticks to only the copper, doesn't run all over the board. So that means there are certain specifications to this printed circuit board. And we can see them, for instance, if we try to get a quote here. So I'll try to order a board that's 50 by 50 millimeters. Maybe I want 10 of them. 2 layers means that there's copper on top and bottom. 1 layer would be copper just on top. 4 layers mean that there's 2 blind layers in the middle. And something really complicated like your motherboard on your computer or your phone has many, many layers. Typically in the kind of designs we do for school projects, 2 layers is sufficient, maybe 4, but that starts to get more complicated. And then the most common thickness for a PCB is 1.6 millimeters, but obviously you can get really thin or thicker if you need something, for instance, stiff or flexible. We'll get this quote. And we can see some other specs. First, it's just amazing how inexpensive these are. We could get 10 of these boards made for a total of $5 plus $20 shipping to the US in 24 hours. Not the shipping 24 hours, but the manufacture. This is crazy. 10 years ago, this would have been hundreds of dollars. So it's just amazing what they can do. Now, what does this get you? This gets you 1 design made 10 times. The maximum rectangular dimension would be 50 by 50. You would get something smaller and CNC to a shape as long as it fits within 50 by 50. They also let you do custom boards here. So we could make it aluminum instead of FR4. Means it would be stiffer and it would have better heat sinking. And then even more complicated styles of PCB. Different kinds of coatings, thicknesses. The standard spacing for these is 6 mil, so 6/1000ths of an inch gap minimum between parts. What can happen here is during the manufacturing process, let's say a hair falls on top of the board. That hair could prevent the acid from etching the copper away, and then you get a short. So the smaller the space you want, the harder they have to try to make sure the board is clean, and it just gets more expensive. And then all the holes that they drill, 0.3 millimeter looks like it's standard now, but you could get smaller holes if you're really trying to pack things in really tight. Solder mask, for instance, I'd like to order purple boards for Northwestern. We can see what happens here. Instead of $10, it's $38. It's 3 to 4 days instead of 24 hours. But it's pretty cool. You would get different colors for a reasonable price and not too much longer. Silk screen's typically white, but if you got a white board, you might want black silk screen. An edge connector, let's say you wanted to make your own USB plug. You could have that built onto your PCB, so you don't need a plug. You just take the PCB and stick it into a USB port. That takes a little bit more engineering on their part. And then finally, surface finish. So a lot of the solder that we use in the lab still has lead in it because lead is much easier to work with than lead-free. But you could never sell a product with lead in these days. So the surface finish and the type of solder they could pre-apply to your board could make it easier to solder or harder to solder, but obviously without lead. And then the via process. So the via is a hole that's drilled into the printed circuit board and then is plated so that you could attach the copper on the top surface to the bottom surface. So those holes are called vias. And then the solder mask that goes on top of those, sometimes, right, because it's a hole in the board, won't what they call tent, or essentially because there's a hole in the board, there will be no solder mask there. And for, I don't know, some reason, for instance, when I produce the end scope, we like to have tented vias so that you don't see little holes in the board. So you could ask them to plug those vias. Makes it look a little nicer, but it's more expensive. And then finally, the amount of copper that's on the board, 1 ounce is standard. That's a 1 ounce per cubic foot or something. Basically, the more ounces of copper here, the thicker the copper, which means the harder it is to heat up the board to solder it, but also the better heat sinking capability the board has. After you make your printed circuit board, you can also have them produce a stencil. A stencil would be a thin sheet of steel with little holes in it, so that if you align that on top of your board, you could scrape solder paste on. So if you're doing a lot of surface mount soldering, stencil would make that convenient. And these guys are now offering assembly service. So if you send them parts, or if you ask for a quote, they can find the parts for you, they could solder it and send it back. Typically, this is still an expensive process. But if you have, say, one chip that's very difficult to solder, it might be interesting to have them solder that one chip and then send the blank board to you and you assemble all the rest. Okay, so PCB's way, it's pretty fun. It's nice to get the quote really fast. They will also show you a render of what your board will look like using the Gerber files. That's also convenient because after we generate the Gerber files from our Eagle files, sometimes Eagle doesn't do what you think it's going to do, and the translation is a little bit off. So you want to double check what the Gerbers look like on a website like this before ordering. So let's take a look at where we are now. I finished my schematic for PIC32 circuit that has a slide switch that selects between a battery and 5 volts from a USB source. I have a 3.3 volt regulator, a power LED, holes for my snap programmer for the PIC, holes for either my LCD or my USB DUARC converter. I've got a big chip that is a I2C IO expander and some components that plug into that, an H-bridge, and then a camera module. What I would like to do is stuff all of those onto a 10 by 10 centimeter board. When I first started these videos, I showed how the PIC would get populated, and I dragged it onto the board. Everything else was auto-populated in this kind of random fashion. So my first job is to set the board size to the size of board I would like to order, then move all the components onto the board, and then rearrange them to try to minimize the crossing of these yellow wires, and then lay down the copper. So most of the boards are ordered in metric, but most of the parts, like the PIC, have 0.1 inch spacing. So I'm going to change my units to millimeters so that I can change the dimension of the board. The yellow line is the outline of my board. I'll do an info on it and change it to 100 by 100. So now I have a square board. Now I'm going to change back to mils for my units with a 50 mil or 0.05 inch spacing for snapping. And that just makes sense because most of these parts have 0.1 inch pitch, so it's a little easier to lay things out in that manner. So the next thing to consider is some of these parts should be near the edge. For instance, here's my USB connector, and the USB connector is probably twice as long as it's shown here because it's supposed to hang off the edge of the board. So I wouldn't want to stick my USB connector right there because how would you ever plug it in? This has to go towards the edge of the board. And now I have to pick where should the power kind of come in. So maybe I'll put it over here. Notice that when I get too close to the edge of the board, Eagle inserts some hashed red lines. It's basically saying if you try to drill that hole too close to the edge, it might tear out. So it doesn't really want me to put those this too close to the edge, even though I want it to be close to the edge. So I'm going to hold Alt to use the alternate spacing and kind of back it off until that warning goes away. And this isn't going to be the final placement. I'll probably move things around a little bit more. But that should be near the edge. Other things that should be near the edge. There's a battery connector somewhere around here. So this guy here, these two holes, this is where my battery will come soldered in. So maybe I should put that near the edge as well. This CP2104, this is the USB to UART converter, and it has a USB cable on the left. So I want to make sure that that's not going to be hanging over the board. So I'll put this over here for now. And when I use it, it will kind of hang off the side of the board. And those pins have to be shared with my LCD screen because we just had not enough I/O pins on the PIC. So I'm gonna put this like right on top of it because I can only use one at a time. So here now, if I plug in my LCD screen, which will also hang off the edge of the board, I won't be able to plug in the USB to UART converter, and so that'll just remind me that it's like I can only use one of those, not both. Okay, what else do we have? I've got my camera module, and this has the most connections to the PIC. So probably what I should do is put the PIC in the middle of the board, and as I kind of move this around, I can see where most of the connections are on the left side of the PIC. So if I rotate, I'm going to minimize the crisscrosses that are happening. So is there a placement of this device with the fewest number of crisscrosses? This looks like an okay placement. I also want to think about, I will use a cable to plug this in, but maybe I don't want to use the cable sometimes when I'm just testing. And so where will the camera hang off? With the ground and the 3.3 at the bottom, it'll hang off towards the left. So this is a good placement as long as I don't put anything else in the bottom corner of the board. Try doing this here. Okay, now I could go back to my schematic and I can look at the PIC, and I've put C2 in the bottom left of my board. Now technically C2 goes between power and ground, so it doesn't have to be near the PIC, but the idea behind these bypass capacitors is that they're as close to the PIC as possible. So I want C2 to be in the bottom left, and C1 to be in the top right of the board according to my schematic. So I'll find C1 and put it up here, and C2 down here, and this 10 microfarad C3, this is for C cap. Now notice that, so once I've moved these parts, the yellow lines are no longer optimized. So if I go and I click this button, the rat's nest button, it will redraw the yellow wires to their shortest neighbor. And my goal is to move these components around so that there's no crisscrossing. So for instance, this capacitor, one side's 3 and one's ground, these lines would crisscross, and I want to minimize the crisscrossing because when I go to connect these with copper wires, if they crisscross, they would touch, and it makes the routing hard. So I will rotate this to minimize the distance between these two components and make all the wires straight. So that's my goal. And I don't want to put them too close because then they'll be hard to solder. So kind of close enough without wasting space. Okay, here's the snap connector. This sticks out vertically from the board, and the pins it communicates with are on the right side. So I probably want to keep this somewhere around here. And then there's a reset button. That close, and it's 10K pull-up resistor. Okay, the slide should probably be towards the end of the board as well. Maybe I'll put that between the two types of power input. And the voltage regulator go there as well. And then my power indicator really go anywhere. And then this is a pretty big chip, but it really only shares 2 pins with the PIC, so it doesn't really have to be close to the PIC. I'm just going to try to get it out of the way here. One thing to pay attention to is the orientation. So this is the top left, this is pin 1, this is pin 1. Your components that have the same shape, try to keep them in the same orientation. It'll kind of make more sense when you go to solder things later. If one is backwards and one compared to the other, and you forget and you make them both the same direction, then you have to desolder everything. H-bridge. H-bridge needs access to the high voltage power. It's kind of the only thing that needs that. So I'm going to try to keep that up here. Kind of weird bug. Won't let me drop it over there. C4 I think is a bypass for this chip. All of these components connect to the I/O expander here. All of these individual dots, they're going to the pins we haven't used yet on the I/O expander. Pull up resistors for the camera. And then where my motors connect. Okay, so now I've got everything on the board. So step 1 is complete. Get everything on the board. Now we're going to try to move them around to minimize the crisscrossing of all the yellow nets, and then we'll try to do the layout. First thing I want to do is figure out why it won't let me drop my H-bridge up here. Bug. Something else I'd like to do is we're going to use N20 style motors to drive our robot around. So they look like this. They're pretty small. I want to see if I can get these on the printed circuit board. So I'll make a U-shaped plastic 3D printed part that holds this down. So on either end, I'll put a hole in the PCB. Let's see if we can fit that on. I've got some calipers and I've got one of these motors. And it's 0.46 wide. From the faceplate to the back where it'd be soldered is roughly an inch. I could draw in silkscreen a box. I'll do it to line tool. Let's pretend that that is a motor. And 4, 6 would make this. 4. Inch. Okay, so that's how big the motor is. If I can slide everything else down, bump it right up to the edge. And I'll drill 2 holes in my board. One. Too high. Whoa. So I'll eventually 3D print a little piece of plastic that's going to sit on top of the motor in a U shape, pinning the motor to the printed circuit board. And then I could have a wheel right here and a wheel right here. And essentially my whole robot could just be this printed circuit board. Now the motors have 2 wires that come out the back. That's where they need to attach to the H bridge. So this is a good spot for the H bridge. And the left motor could be A and the right motor could be B. I wonder if this version, the free version of Eagle here, doesn't want me to put things outside of a certain boundary. Okay, so let's keep going. We've got all these. Dots. Let's drop those closer to where they're supposed to be. These holes are just in case I have these pins on the camera and the IO expander I don't plan on using, but maybe I will for some reason in the future. So I just want to make sure I don't block myself out. Oh, this is weird. There. So you may notice I'm putting stuff on top of silkscreen layers. I'm going to move all the silkscreen around later. Right now I'm only focusing on the yellow lines and the green dots and the outline, making sure none of the parts overlap each other, but they can overlap their silkscreens because we can move that easily later. Okay, so I'm getting happy with this part of the board. Okay, so this 10 by 10 centimeter board, it's quite big. Normally, we would have to pack our components in a lot tighter. Now this is still going to be a difficult route because we've got all these crossing yellow wires here. But I don't think it's going to be too bad. And in fact, I could probably add more to this circuit board. It's a shame to leave any empty space like this because maybe in the future I'd like to add more chips. Not that we have many pins on the PIC to work with, but we have the pins on the IO expander. Maybe we want to add more buttons or LEDs or something. So one thing I could do here is I could stick in an array of holes, kind of like a breadboard, and leave myself a prototyping room. And it looks like maybe 1, 2, 3, 4, 5, 6, 7, 8. If I had an 8 by 10 area here, I could fill in. So let's save that and we'll go back to our schematic. And I'm going to add some components. I'm going to add a connector of 8 holes. And I'm going to, let's put 5 of them, 2, 3, 4, 5, kind of like a breadboard. If that, go back to this design just to make sure they all fit. Okay, and so I could probably connect those 5 in a row, just like a breadboard, and then I can leave a gap, and I could copy this and put another one of them here, and I'd make myself a little breadboard. So let's go do that. We have to make the connections. So that's one row of a breadboard. 7 more. Okay, let's check that out in the board. And we can now see the yellow lines that go across. So nice little breadboard area. Let's copy that. Here. Maybe I'll add 2 more on either side, kind of like rails, for more power. So these ones I'll connect like power rails in a column. That's kind of annoying to do. Copy that. And we'll make one of them 3.3, and we'll give ourselves 2 grounds. And then I'll see if I could get V in to stretch down there in case I need more 5 or 6 volt connection. These 2 are ground. It's always nice to have extra holes for grounds and extra power holes, in case you found that you made an error and you need to tap off of a power supply somewhere. I forgot to connect that. 3.3 volt. There we go. Okay, and then one thing I'd like to do is get rid of all the silk screen around these holes. So this is the 1x08 in my library, so I'll go back to my library. I'm going to open up the 1x08. I'm going to trash all these guys. Okay, so now it's a little bit cleaner. I'm going to trash all of their names. And then to remind myself that the 5 in a row are connected, I'll put a silkscreen line on top of them. And then of course I need to remind myself ones are which. Let's go over here. Okay, all the components are where I like them. Now we just have to lay out the copper. So there's one way to do this that I would consider maybe cheating. That would be using the auto router. That's a button you could press and it will automatically figure out how to connect these wires. But you know, it's not going to do it in a very sensible way. So I still like to route everything by hand. That means we have to manually connect all of these yellow wires point to point. But there's some cheats that we can use. So the first is that a lot of the connections are ground or 3.3 volts. So for instance, if I look at this connection, this is all the 3.3 volt pins. All those need to be connected. And if I look at this point, these are all the grounds. One method of connecting these is to use what they call a ground plane. So a ground plane will do two things for us. One is that ground can act as a nice heatsink. So adding a lot of copper to the board as a big plane will let us do some good heat sinking. And the second is that it will automatically connect all these for us. So the way I'll do that is I will grab the polygon tool, and on the bottom plane, I'm just going to draw a big square around the entire board. And I'm going to call it GND. And then if I hit the rat's nest tool, it will automatically connect only to things that are ground. So these green circles here are not touching the blue because they are not ground, but this one is. Let's look at the options for this. So we do an info on that edge. We get to see that the thermals option is checked. That means that only little lines are connecting the grounds to the ground plane. Otherwise, it would be very hard to solder because if they had a really good thermal contact to this plane, it would take a long time to heat up. So while it is electrically grounded, thermally it's not great, but it's okay. Orphans is not checked. Orphans is if we somehow cut off a section of this, it would no longer stay filled in. Maybe we'll see that in a bit. And then the isolate parameter is a thing we probably want to change. How much of a gap is there between things that are ground and not ground? I like to put at least 10 thou. Let's do a little more. Make sure I'm hitting the right thing on 124. Yeah, really big gap. Okay, let's keep that for now. So now all of my ground connections were just automatically made for me. I could do the same if I wanted to. I could make a plane on the top surface on red and have all the 3.3s automatically connected. But let's see how hard it is to do those manually. I'll hit the eyeball tool. Now find 3.3. And I'm just going to try to go point to point and connect these. Seems like I can start at the regulator and go to this LED, and then go to here, and then go here, and then branch around here. So here's how we do that. We select the route airway tool, and I'm going to start on the top side of the board, and I have a width of the copper. The wider the trace, the more current it can handle. Now, none of these traces are going to have that much current in them, so I'm not really concerned about them burning up. But there are trace width calculating tools out there that will tell you, given the width and the amount of copper you're using, we're using a 1 ounce, standard board here. It'll tell us the max current, and then we can adjust the width in case there's a lot of current in a particular trace. So when I'm doing this air wire, it won't let me click on things unless it starts at a point. So I'll say I want to start there, and I want to end there, and it's not going to let me touch things that I'm not allowed to touch. So I'll go from 3.3 volts from the regulator to this LED. And I'll go from the LED to this pull-up resistor, and from the pull-up resistor to the snap. I don't particularly like the way I did it there, so I'm going to try to guide it in this direction. Let's see, where do we go next? Eyeball tool. So one thing I can see is, as I try to route this one, is that I go up here, I'm going to cross the MCLR wire. So I kind of want to come in between here and finish here. So I leave this path, I can do this one right now. MCLR can go straight to there, and that can go to the button, which goes to the pull-up resistor. But one thing you could probably tell here is that horizontal lines and vertical lines eventually need to crisscross. For instance, this VN pin now needs to somehow get across these red ones. So a Manhattan style would be probably a better idea. Any horizontal line being in red and any vertical line being in blue would make it easier to get crisscrossing lines across each other. So we'll see that probably in a second. I'm going to continue doing the 3.3 volt line. There. Here I can go under the H bridge. As long as I'm over here, I'll do this pull-up resistor. So now I need to somehow get the 3.3s routed down here. So I guess I'll sneak along this direction. I don't want to continue this one this way because it's going to cross those wires. So instead I'll jump around this way. Yeah, I already see there's going to be a lot of beeping coming up. More pull-up resistors. So here's some potential crisscrosses coming up. I need to get this 3.3 up here, but these going downwards in that direction will need to cross it. So here's the technique. I'll go across in red, and then I will switch to the bottom layer up to here, and then I'll switch back to the top layer. And if I hit the rat's nest button, it shows that I just cut away some of that ground plane to insert that blue wire. Doing that will make it easier to connect B6 and B7 later on. Okay, so how did I do? Did I get all the... Nope, there's still some more 3.3s. And in a super messy area. So let's try to do these now, but they may have to be moved later. I'm going to do these on the bottom. Try to keep everything else on the... Let's move this out of the way. I'm going to delete all their labels. Yeah, this is definitely going to be the trickiest area to do. Yeah, sneak this one. I can't get it through there. Well, I think I'll finish the 3.3 after we get these more complicated ones done. Okay, so let's come back and do some more power connections. So here's the initial ground coming in from the USB cable. I need to, because it's a surface mount component, I need to get it from the top into the bottom with via. And we can see that the detection is saying that this pad is too close to the circle, so we can fix that in the library later on. Here's going to be a tricky one, getting the 5 volts from the connector to the switch. So I'm going to rotate the switch, them on the right side. I don't need any labels. I'll leave the value of capacitors and buttons. Okay, sorry for the distraction. So I'll just try to get these easy ones out of the way first. So here we could see a crisscross that needs to happen for that to get there. Bring it here. And I think I'll just move this guy to the bottom layer. So I think to get this 5-volt around to here, I need to move that 3.3 that I originally done. So to remove that wire, I use the rip up tool. Okay, so we're starting to get somewhere. Almost all the easy ones are done. This one's going to make a lot of beeping noises. Sorry about that. Oof, okay. Let's start with these guys. These are kind of tricky, but shouldn't be too hard. Be able to sneak them through here. It doesn't really want to get through those individuals. I think instead move these guys up. Their placement doesn't protect here. I will switch them to be on the bottom here. And we'll go one by one. That way. So sometimes this is called fan out, although that's usually a different kind of chip, but essentially getting all these to go out in parallel. Okay, so now we're starting to approach what looks like probably the difficult ones. I think what's going to make it easier is if I move all my breadboard stuff over. This V in here is going to be a little silly, but that keeps it out of the way. Let's look at these two. This one's not going to be so bad. All these to the bottom. So I'm just going to start to just grow them from one side. Good. And anything that needs to go on the left, start to sneak under. And then I'll try to keep things going left and right. On the bottom. These top four need to go all the way over there. So I'm just doing my best to keep red wires going up and down and blue wires going left and right. Hopefully that saves some pain in the future. This kind of wiring is called Manhattan wiring, keeping things in a grid. Okay. Okay, starting to get there. Okay, we're slowly building everything towards this complicated area. I'm trying to keep everything on the outsides going outwards to save space. Better get these guys across sooner than later. So here's a dangerous thing that's happening. Here's a ground pin on the PIC, and I've been slicing up this ground plane. So now the only ground connection is there. We just want to make sure we don't orphan that pin. I think I've got everything around it, so far it looks good. We'll try to get this one straight across underneath. Yeah, getting pretty tight. .3. Okay, I think we're very, very close now. Just need this last power pin. Go under. Okay, so that was a lot of fun. I'm gonna do some housekeeping, put some labels on things. So this will be motor A, that'll be drive A, this will be drive B, or motor B. Got my user button, reset button, got all my LEDs, so I've got my resistors labeled. My breadboard areas labeled a little better. Okay, now the Eagle software wouldn't let me touch things that weren't allowed to be touched, but they'll let things get real close. We'd like to do an automated error checking just to make sure nothing is too close. And the way we do that is by running a file called a DRU. And that's under the DRC. So I'm going to say DRC, and I'm going to load a DRU file. And I've loaded a SparkFun DRU file onto our Git page. We'll open that and say check. And it's going to point out all the things that generally are just closer than 0.006 of an inch. Okay, so it's picking up things that are too close. So 2 in the USB connector, 3 in USB. Thought that looked a little close. So we're just going to shove things around using the Alt key. Over see. Let's go back to this drawing of the USB connector. So these holes should definitely not come within one width of Yeah, so these holes are just too big. Let's make them smaller. That looks better. The danger is that we make this hole too small and then the leg doesn't fit in. Oh no, it looks like picking out all of my vias, saying that they're too small. Okay, so here's a good example of how we can increase those. There's a change button here, and so we can say change the diameter. Let's figure out what these are first. A 13 drill. Bumped it up to 19. Let's see if it still complains. Yeah. Five makes go away. 3 makes go away. It's too small. 21's okay. We're going to change them all to 21. Run the DRE again, make sure. Got this one. Okay, so I want to change the drills to 21. Drill 21. Okay. Probably could have caught this error earlier if I'd run the DRU after just doing a few wires. Move some things later on. clearance issues. Okay, so this now passes the automatic inspection. None of the wires are touching things they shouldn't touch. They're not too close to things they shouldn't be too close to. Potential bugs that are introduced by me may be making those holes too small so we can't get the legs in, but we could always drill them out and push them in if we had to. And then, of course, any of these wires that I should have hooked to other pins, that could be a bug. It's not much error checking Eagle can do for that kind of logic error. So, a couple things we could do if we were really concerned. We could take individual connector holes like this, and we could add them to every pin on the PIC. And then if one of these connections was bad, we could cut it with a razor, and then using the hole that we added, wire to somewhere else. Those are called green wires. I'm just going to cross my fingers that we don't need any of those because I don't really want to add one to every single pin. And then we've got this breadboarding space down here. If anything major is wrong, we can always rewire things down here. Let's see, I've got some labels for my motors. The silkscreen layer is free, so I should always add something like my name, date, what this class was. So this is for 450. Let's just put 2021. So liberally use adding text all over the place. Anything you think you should label to remind yourself of what does what. For instance, the slide switch, when it's on the right side position, is going to be USB power. Down eyes a little. And when it's on the left, it's going to be on battery power. The battery's got a positive and negative side, a red wire and a black wire, so I should probably label those connections to remind myself which goes where when I solder. And that's a good thing to do for anything that is polarized. Add a plus sign to the positive side. For instance, this big capacitor here, oh, they already put the plus sign in to remind us which way it goes in. I think that's the only other really polarized component. The motors don't really matter. The big chips have these indents. The snap, I drew a triangle. I'm just scanning around now looking for any obvious bugs. I don't really see anything. Close wires over here, but the error check didn't find anything wrong, so we'll keep that. Okay, let's cross our fingers. Now that the board is designed, we need to generate Gerber files. Gerber files are instructions that the robot that makes these, that the manufacturer uses to lay out the board. To do that, we go to the CAM processor, and we need to select a .cam file. So we say open CAM file, And I've provided one from SparkFun. And we can go through just trying to double check that they're doing the right thing. Need to give some rings, but that's okay. And here are the files they're going to generate. Each file is a different layer. So a layer for the top copper, bottom copper, top silk screen, top paste, bottom silk screen, top solder mask, bottom solder mask, and the drill file. So this should be 712. Process job. And I'm going to put them into so now in my folder, anything with all caps, GPL, GPO, GBS, GTL, GTO, GTS, and the TXT file. These are my Gerbers. So the B's stand for bottom layer, T stand for top layer, L is the copper, S is the silkscreen, O must be the solder mask, and then the TXT file is locations of all the holes. Copy those. Output files. I'm gonna make a new folder called Gerbers. Paste them in there. I'm gonna zip this whole thing up. Now I want to see if this zip file will upload and verify that the file, the Gerber files look like the board that I designed. So let's try Seed Studio. We'll go to their Fusion page. I'm going to order some PCBs. Add Gerber file. Select my zip. And go to their Gerber viewer. And here we can see my board design. So what should we look for? So the text file were the holes. Usually where this often messes up are two different things. One, the silkscreen layer doesn't match. And two, the holes are scaled improperly. So if I turned off the holes and then turned them back on, looking at these purple ones, all the holes match, so that's good. Not sure what generated file doesn't even do anything. But one thing that I do see is missing is, for instance, the labels for the values of my resistors and capacitors. If I turn off the top silkscreen layer, they'll go away. So for some reason, they weren't included in my silkscreen. So let's go back to the cam. And I'm going to look at the top silkscreen. And the things that are being included are T21 and T25, but not the layer T27 T values. Let's add that. Conversion. Up. I guess all of these are legacy, so I'm just gonna update them all. You should probably do this too. And top silk screen, key place, I'm gonna add T name and T value. Now say process job, servers folder. It was just remade. These must be the old ones. Okay, I don't know why they have names, but the stuff's all there. I'm going to stick these in a compressed zip file. And we'll try again. Okay, so now I see my resistor values, capacitor values. One thing I don't have are some plus signs to remember which way the LEDs go. I should probably add a plus sign right there. And where's it? Here. You wouldn't want to sort those in backwards, get it wrong. Got our labels for the power on the breadboard area. I'll probably label that this is the PIC and this is the I/O. So that's about it. Design your board, make all your errors, keep editing. You can obviously keep doing this forever. Don't drive yourself crazy. Take a screenshot of your schematic and your PCB, upload that for your homework assignment. I will order these boards, and hopefully in 2 weeks we have them and we can start soldering and compare this to our breadboard.